In the last lesson, our focus was on differences in the solar constant. Here we move on to the second of those controls on Earth's temperature, that is, the albedo. Albedo is a somewhat unstable part of the Earth system. And the reason I say that is we tend to think of the surface temperature of the Earth as being a function of the albedo, among other things, of course. But of course, albedo, because it relates to how much ice is on the planet, is also a function of the surface temperature. And so these linked relationships provide a means for there to be positive feedbacks, where, for example, if you decreased the surface temperature, you would increase ice extent and increase albedo, which would then cause the surface temperature to decrease, which would then cause albedo to increase, etc. This instability was explored by simple climate models known as energy balance models. In these models, researchers would start with a warm Earth with very little ice on it. We can show that schematically here with just open ocean, no ice, ignoring the continents for now. And on this plot of the latitude of ice extent versus global temperature, we'd place a point somewhere up here. As atmospheric CO2 dropped in the model, global temperature would drop and ice would start to grow toward the equator. So now we see small ice caps at both poles and open ocean. Then, as CO2 dropped further, global temperature would drop and ice would grow closer to the equator, something like this, extending now toward the mid-latitudes. So far there's nothing unexpected about these results. But what happens as ice starts to extend toward the equator is that at first a small amount of the incoming solar radiation is reflected, and then more and more is reflected. And so you get this positive feedback where larger ice sheets reflect more incoming sunlight, lowering global temperature and allowing more ice to grow. And so in these energy balance models, as soon as ice reached the mid-latitudes, the model became unstable and ice immediately propagated all the way to the equator and global temperatures plummeted. This is to say that there is no stable state in these models where there's ice in the mid-latitudes. As soon as ice gets to a threshold point, it jumps to the equator, creating what's known as a snowball. More sophisticated models more recently have shown similar behavior, and one way of schematically showing this behavior is with a so-called bifurcation diagram. In this diagram, we have a hypothetical warm world with either high PCO2 or a high solar constant. Taking the example of PCO2, as it starts to go lower and lower, the world starts to get cooler and cooler. And this happens in a fairly gradual and reasonably linear fashion for a while. But then, as the world gets to some critical temperature, at which ice line extends to some critical latitude, the world jumps into a so-called snowball state. And to get out of that snowball state is no easy trick, because you now have a world that's covered in a highly reflective material. And so you have to increase CO2 higher and higher and higher before the ice abruptly melts and you're returned to the warm world. This was thought to be just an interesting exploration of climate in models, until evidence for such a snowball state started to pop up. In the late Precambrian, in a period called the Cryogenian, geologists found evidence for extensive ice sheets from around the world. This evidence included striated bedrock that's known to form under glaciers and ice sheets. They also found telltale glacier deposits known as diamictites. These are unsorted sediments that were deposited at the front of the ice sheet as it bulldozed across the landscape, and the clasts within them are striated from interactions with the bedrock. Putting this evidence together, we see that for one of these glacial periods around 700 million years ago, there's evidence for ice sheets in places all around the world. Similarly, in the more recent of these glacial periods, around 650 million years ago, there's also evidence in even more places. As you may know, the continents are constantly moving across the Earth's surface, and so then the question becomes, where were these glacial deposits when they were formed 600 to 700 million years ago? We can get an estimate of this through paleomagnetism. If we treat the Earth's magnetic field as a fairly simple dipole, we see that the inclination of the magnetic field is a function of latitude. At the poles, the magnetic field is oriented perpendicular to Earth's surface, and at the equator, it's essentially parallel to the surface. When sediments are deposited or when magmas crystallize, magnetic minerals within them orient parallel to the Earth's magnetic field. And so we can get an estimate of the paleolatitude of these deposits, that is, the latitude at which they were deposited, by measuring these magnetic properties. If we look in more recent glacial deposits, we get basically what we would expect. The inferred latitude of these glacial deposits is somewhere in the mid to high latitudes. But in this period called the Neoproterozoic or the Cryogenian, in this time called the Neoproterozoic, and in this specific period called the Cryogenian within it, we see that the paleolatitudes are biased toward low latitudes, suggesting that these ice sheets actually extended to very close to the equator. Putting these glaciations on a timeline, we see that these so-called snowball glaciations occurred toward the end of the Precambrian, right here, and also, as I mentioned in the last lesson, at the very end of the Archean. Both of these are times when atmospheric oxygen was rising. They're both also times when there were very interesting steps in the history of life. For instance, at the end of the Precambrian, there was a rapid diversification of animal life. So how does a snowball Earth event work? Well, we don't precisely know, but the general hypothesis is that there's global cooling for some reason. This cooling proceeds so that you get a runaway ice house and ice sheets extending to the equator. As a result of this, you gradually have slower weathering and less calcium supplied to the ocean. This means that you're taking less carbon out of the atmosphere and burying it as calcium carbonate. We'll talk about this more in the carbon cycle unit as a part of this class. The main point is that you've disrupted the sink, that is the removal process for carbon dioxide from the ocean atmosphere system. At the same time, the primary natural source of carbon dioxide to the atmosphere has not been reduced. That source is from volcanic emissions. As a result, over geological timescales, that is hundreds of thousands to millions of years, carbon dioxide builds up to very high levels in the atmosphere. Again, because the source remains relatively constant, but the sink, the removal process, has been greatly reduced. Once the CO2 builds up high enough, you get a very rapid deglaciation and a very, very warm climate. We still have many, many important questions that are unanswered about snowball events. We don't know precisely what caused them. We don't know why there haven't been any in the last 600 million years. And we don't know why they're correlated in time with the rise of complex life toward the end of the Precambrian and the beginning of the Cambrian period.